Okay, let's start. Welcome again. One announcement. Next week and the week after, we have no lectures because this time I'm away. But then we can come back on June 10th, I guess, if it is okay. So to the last time we checked that it is okay to continue summer and also for you, right?
So throughout the whole summer or throughout June?
Yeah, on and off, I don't know. So the decision is that we want to complete this part, and this part takes just 2-3 sessions, and I guess it should be finished in June. Yes. Okay, so that's the first thing, and so therefore I have to be just careful today to cover everything that I want to say before going to logic. So, okay. Let's start with, let me write it down here. So if you remember, we had this okay, why not? So we had this category C, we had this category set to the C opposite, we had this Yoneda functor, right? That is just an embedding. And also we had the Yoneda lemma. That was this guy. Say Yoneda of some A and some F is in natural correspondence with F of A, and for now that's it. And then we said something about sites. So add one coverage, and then you restrict yourself to the category of sheaves with respect to this site. And by this category, I mean objects are sheaves and morphisms are all natural transformations. So therefore, this guy is just a sub category of all pre-sheaves. So I'm restricting just my objects, but all the morphisms between two sheaves, I pick them up, right? So it's just a full subcategory. And the task of today is just to prove that this guy for any C and J is a topos, right? And this completes our construction of the first construction of toposes, right? Okay, and also we want to understand the connection between this guy and C, say, and some computations here because they are kind of useful. So another thing that I have to say is the propositional comparison that we had, and that is kind of useful. So it is possible to do these things with no morphisms and changing set to just 2, 0, 1. Either you have an element or you don't, and you don't care about the elements. So then we had, if you remember, just to restrict this C to poset, and then my Yoneda, and here I have two P opposite. So this is just the poset of all, decreasing maps, say to 2. This is just equivalent to all downsets. And this Y of, say, A is just the downset of A. Okay, so then what is the sheaf counterpart of this example? So for the sheaf counterpart, I choose my P and its order because I need some coverage here, right? So I choose it to be a bounded distributive lattice. And then the coverage is, as we had so many times, A1 up to AN simply means, so this is a covering family if it's covering if just the union of AIs is A. So the join is A. And since it is distributive lattice, we saw that, it's a coverage. So what's a sheaf in this sense? So pre-sheaf is a downset. Sheaf is some sort of downset, but it must have the sheaf property with respect to the coverage, right? And this means that if you have just elements, okay. So if you have, based on downsets, if you have a downset, writing down the sheaf condition simply says that if all of these guys are inside your downset, then this guy should also be there, right? And so a downset with this property is ideal, right? So we know that downset D closed under finite joins, right? So what I'm saying is that downset is my pre-sheaf in this setting, and ideals are my sheaves, right? They are kind of analogs, right? So just by changing, so they are not really sheaves, and I'm changing everything in an analogous way. So, okay. So now let's play with this category. So whenever I say category of sheaves, I mean just fix your C and J, right? I don't consider all of them at the same time, right? So sheaves, I mean sheaves with respect to some site, but I don't say what is the site, right? So the first thing that we saw before is that this guy, which is an object here, and therefore it is a functor, and it is just a constant functor, right? Mapping every object to just a singleton star and all maps to identity of that star. So that functor is a sheaf, right? We checked it before for any coverage because you have just one element everywhere, right? So what I want to say today is that this guy is actually, okay, it's an object here. It is the terminal object, right? So this category has a terminal object. And the reason is just simple, right? So, so to show that it is terminal, it means that I have to show that for any other f, there exists a unique map to it. And map is natural transformation, so it is just one. So I have to define it for any a, f of a to just singleton. So I have terminal then. The second thing that I want to say is that the product it doesn't matter here, right? So the only important thing here is that this guy is a sheaf and it's an object there. And to check that it is a sheaf, so you can see that it doesn't matter what J is. So because you have just one object everywhere. So any compatible family is just the family of that one object. You can find, the gluing with one object. So everything is just kind of degenerate. So the second point is this. If E and F are sheaves, then say E times F is also a sheaf. So what do I mean by times? So this is just a product of two pre-sheaves say, because these two guys are pre-sheaves, therefore they live as objects in set of C opposite. Here you have product, because this category has all the limits, we check that, and the product is simply just the pointwise product. So you want to define the product of these two as H, you define it simply of any A as EA times FA, and similar for the morphisms, and it is just easy to check that H is just the real product. What I'm saying is that this product, either as a product in set to the C opposite or with this explicit description, it is actually sheaf, right? So how do I know that? Just check the sheaf condition, right? So it is just very easy. So whatever the covering family of some A is, so A1 up to something. So what I have to show is that if I apply this functor to this guy, so I get something like this, right? So let's compute it. E1, FA1, etc. EA times FA, and the map. The map is just, E of the first, F of the second. And so the only thing that I have to show is that whenever I have a compatible family, I can just find one gluing here, a unique one. And a compatible family here is just the first elements are compatible, the second elements are compatible with each other, right? Because you can open up everything. So these are just pairs. And so the first is a compatible family with respect to E is a sheaf. You find your element here, the same for F, right? So the main thing is that whenever I have elements in the product, I can just open up the data. So this means that this category has all products, has all at least binary product, right? And make no mistakes. So it does not. Just the fact that this is a sheaf, it does not mean that it should be a product, right? In this case, it is, because sheaf, the category of sheaves is just the full embedding. So it is just a full subcategory, right? So if you want to show, let's say that I have a category D, full subcat of some category E, and then I pick two elements here, EF, and go there, compute the product, and the product actually exists, lives here. Then you can show that this is actually product also here. Simply because what is a product? You need, projections, and it should be universal, but everything is just about maps, and all the maps here are just maps there, so who cares? Okay, so then I have all the products in this category. And exactly, yes, exactly. So there is nothing special for, to have binary. So you can have any number of things in your product, right? And even better, you can say exactly the same argument with more care for any limit. Right? So the whole idea is that not product, but if I put some limits here, I know what is an element in the limit. I can open it up. It is an element here, there, with some compatibility condition. So that's just fine. So therefore, you can show that you have all limits in this category. And also better, you can compute it as in set to the C opposite, or technically just local, right? So that's good. Okay, so this is just the first condition, even better, of being a topos, right? Having all finite limits, and I have even all limits. That's easy. What about co-limits then? Please change. Okay, so do I have the same thing for, say, colimits? Let's say like this. So this is my category. And let's say that E and F are two sheaves. And then is the coproduct also a sheaf? Because if it is, then that would be very good, right? So I can compute everything quite easily. Is it? Who knows? No. And we already know why. What is the example? Let's say, so not in general, of course, sometimes it is, but not in general. So, so is not necessarily a sheaf. Example, work with this sheaves of X, which is just sheaf with respect to opens of some topological space, and J is just the obvious covering of union. And here we saw that the only constant functor that's a sheaf is just delta star, right? And no other constant functor is a sheaf.
Can you say it again?
Yes, so C is just the open, covering is union. So here, the only constant that's a sheaf is this guy, right? So, okay, always this guy is a sheaf. So plus delta star plus itself is what? In set to, say, OAX opposite, right? So if you compare this, it is just pointwise. Simply, it is just delta of two elements, right? Singleton plus singleton, right? Everywhere two. And this is not a sheaf because it's constant, but it is not singleton. So sheaves are not closed under co-products, not closed under co-limits, not necessarily. This is just the best example. Even better, or I don't know better, but what is the initial? Initial even, initial in set to the C opposite is local, is pointwise, I mean. So it is just delta empty, right? Everywhere empty. And this is also not a sheaf because it is not singleton, and even worse because always a sheaf on empty should be a singleton, and this is just always empty. We check that. So if F is a sheaf, F of, so F, okay, so this is O of X, and therefore I have F of U's, right? And one of them is F of empty, and this guy should be a singleton always. Otherwise, it is not a sheaf. We check that. And this guy is not a sheaf because it is empty always. So no initial, no coproduct, no colimits. That's bad. It doesn't mean that this category does not have all these colimits. It simply means that the colimit in the bigger category is different from the one in the smaller, right? Maybe.
But it should have.
It should have finite colimits at least, yes. And therefore, we know that it has finite colimits. And even better, it has all colimits. We will see. And we will see how to compute it. But before that, I have to say two things. One is, what is the problem really? Because, okay, we have counterexample, but you can say that let's just try it, right? So let's try to prove that it's a sheaf, and where is the problem? So if you try to prove that this guy is a sheaf, you write this down. Yes, thanks. You write this down. And then you can see the problem. If I have a compatible family above, some of the elements come from E, some from F. So I cannot get a compatible family of E or F. which means that I do not have enough elements here, right? This covers all compatible families in E. This covers all compatible families in F, but there are some mixed compatible families. So you have to extend this guy to also have those things. If it is not that convincing, let's try this example then. So I said that if I have sheaf, then the limit of sheaves is a sheaf, right? Equivalently, it means that the intersection, any intersection of ideals is an ideal. Of course, because it is just a closure property, right? It should be closed under something. The intersection of some ideals, whatever the intersection is, the limit is, it is an ideal, right? But the same is not true for co-limits. The union of two ideals is not an ideal. Because if we do the union, then some element comes from one, some elements from the other, and the join is not in any of them, right? So how to solve the issue? Usually we do what? We do the union and then make it an ideal, right? Find the least possible ideal, right? Add whatever you need. And this is just like that, add whatever you need that I said here. So is it possible to do it even generally? Because here, whenever I have a downset, I can make it the smallest possible ideal extended, right? So you can do exactly the same game with sheaves. If you have a pre-sheaf, you can just cut it up to be a pre-sheaf to a sheaf in some smallest possible way. I will explain that later, but for now, I have to say something. So again, this board, the third thing that I want to say is that if you have two sheaves and you have one map, which is monic in three sheaves, is monic. If it is monic as sheaves, as in the category of sheaves, right? So you have two sheaves, of course, but one map between them, and monic here and there are the same. Again, being monic is kind of relative thing, right? It depends on the whole category. So it may change, but in this case, it doesn't. And why is it important? Because later I want to investigate the sub-objects here, right? All the monics to interpret logic. And here simply it says that, okay, go there. And there everything is just pointwise. Therefore, it is just some subsets, of course, compatible with the morphisms, right? So how do I know that? So one way is just to try to prove it. And so this way is easy because this guy is bigger, simply, right? So the main thing is this way. How to prove it? So here is my trick. So I do some trick that is useful actually everywhere else. So I write being a monic in terms of limits, and then since I can preserve limits, then I can preserve the monic, right? And here is just the lemma. So the lemma says that in any category, in any cat D, a morphism F from say A to B is monic if what? If this A identity A, if this is a pullback. That's easy to check, right? Because of course, all the time it is commutative because these are identities, right? So being a pullback simply means that whenever I have something here and two maps, say G and H, such that the composition are equal, so FG equals to FH, then I should be able to factor it uniquely here. And uniquely here means that F and G, so even factoring means that F and G are equal. So G and H are equal, right? So it is just another way to writing down being a monic. And so since any functor just preserves, any embedding, any whatever preserves identity, if I preserve just the limit, the pullback, then I preserve the monic. And the bad thing is that the same is not true for epics. So again, one way is easy, right? So if something is epic here, if it is surjective pointwise, then it is epic here, because that one is just bigger, but not the other way around. So it is sometimes possible that I have some epic here, which is not pointwise surjective, right? One example. So you may think that, okay, that is just formality, whatever, I don't care. First, one example, then I want to explain how important it is. So first, what should I do? I need some category of sheaves, say this, why not? For some X. And then I need two sheaves, right? So I pick for one sheaf one. This is just that guy. This is an example of the following. So I want to provide a morphism, right? From some sheaf to one in this category, such that it is epic here, but in pre-sheaves it is not epic. So it is not surjective pointwise, right? How to do it? So first, let's say, okay, think about this map that we had before, right? So this map. So what is the, so P, whatever, okay. So P of any theta is a CI theta, right? So it simply maps theta to, so the number theta goes to this point, right? And we saw that this map somehow locally is homomorphism, right? So if you are just around some point, just close enough, then you see that everything is in one-to-one correspondence, right? Meaning that locally you have the inverse of this function, which is just a function that reads a node and find out the angle. So angle is locally well defined, but not globally, because globally it is not continuous, 0, and then it should be 2p or 0. 2p means, multi-value, 0 means non-continuous, right? So we saw this guy. And so let's pick F, the sheaf of sections of this guy, meaning that F of any U is, so my X is S12 then, S1, S12. Fu is just the set of all sections of P over U. So these are just all possible, say, angle maps on U, right? And sections, if you don't remember, it is just, you know what it is. So,
Sorry, U is a Subset of the middle.
Of S12. S1. Yes. Yeah, here's the picture. So let's say that this is my S1. This is my R, right? This is the map P. And then U lives here. And above U, you have all possible angles, so many of them, right? And then any section is just a continuous function here. Right? For any element in U, it picks one possible angle, right? It reads something like this, right? This is my U, and then it reads one element here, a section, and assign some theta of this.
Should I? Section.
Yes, but I can define it again. So section is something like this, but formally it means that it is some map S from U to R, such that if you go there and come back, right, is identity in U. Right?
Oh, decompose that.
Yes.
Okay. Okay.
So, and of course, F is just a functor, it's a sheaf, we saw that, right? So sheaves of sections. So it's a sheaf, and of course there is a map here because it's a terminal, there is just one unique map, right? Just collapse everything to 0. That star. And my claim is that first, this guy, okay, the first thing, this map, the unique map, is not surjective pointwise. Which is equivalent to is not a peak in set to O of X opposite as pre-sheaves, right? And the reason is just simple. So do you know why? So I have to find one U such that F of U to star is not surjective. What is that U? So this pointwise simply means that this is not the case, that this delta star. It's not the case that for any U this is surjective. And how do I know that? Exactly. Pick U as the whole S1, right? So simply, there is nothing in F of S1. There is no section, right? There is no continuous angle on the whole space. Locally, yes, but on the whole, there's none. It needs a proof, but intuitively you see it, right? So this F of S1 is actually empty, right? There is no global section. And therefore, of course, empty to star is not surjective. So all in all, simply it means that you have local sections, but not global sections.
This is an example of the difference between the topos and the included sheet.
What do you mean?
Oh, maybe not. No, it's not.
That-
No, this is, well, you said what is an example of.
Yes.
So it's an example of
Difference between epics in pre-sheaves and sheaves.
this.
So what I'm saying is here that this map is not epic in pre-sheaves.
It is in.
Sheaves.
What is the sheet?
Now, these two guys are sheaves. This is just a map between them, the natural transformation between them, right? So in both of the settings, when you think of it as a pre-sheaf map or sheaf map, always these two are sheaves. So, and you have a map. So you read this map as a map inside the category of sheaves or inside the category of pre-sheaves.
So there should be one version of this example, which is epic, one version.
No, just one map, fixed one map. it is epic in one category, not epic in the bigger one.
So, sorry, can you say again which category it's epic in?
So one category is just the pre-sheaves, the other is sheaves.
So which one's it epic?
Sheaves.
You're showing it's not epic in pre-sheaves
Yes.
because
In pre-sheaves, yes, in pre-sheaves, epic means epic pointwise. So for any u, f of u to star should be epic as a map between sets, which means surjection. And this is not a surjection because this is empty. Right?
And what is the context in which this is epic?
What do you mean?
You said you want to say that epic
In sheaves. Yes. So it is not epic in pre-sheaves. I showed that. So I have to also show that it is epic in sheaves. Yes.
And
Okay. So I have to show also that it is it is epic in sheaves, but there is one important thing here, right? The important thing is that this difference between epics here and there actually captures the idea that there is no global section, right? Which is extremely important in geometry, right? And then people go further, right? It is not just enough to know that there is no section. You want to measure it, how much you lack the section, right? The global section. And then people develop the cohomology theories, right? The sheaf cohomology theory to understand, in some sense, how much this map is not epic. Okay, so I will say something about the logical context of it, but first I have to say that why it is it's an epic in sheaves. Should I really? Yes, that's good. So to epic, this guy is epic in sheaves, and the reason is this. So let's say that I want to show that it is epic, right? So let's say that I have this, I have one, I have two maps, say alpha and beta, to something else, to some e, and such that alpha composed with this equals to beta composed with this, and then I have to show that alpha equals to beta, right? This is just the definition of being epic. So the point is that usually how to prove something like this, if you have surjection, if these two are sets and you have surjection, right? So then you can say that alpha and beta are equal on some elements because that element is a surjection, that this is surjection, this element comes from something, therefore you know it, right? So I cannot do that for any u because this map is not a surjection, right? For any u, but I can do something of that sort. So let's say that I want to show that alpha restricted to u equals to, so I mean alpha u equals to beta u, right? And the problem is that f of u to star is not surjective necessarily, right? Okay, who cares? I can cover u always with some ui's small enough such that this map is surjective, right? Because I have local sections. So go there for any f of ui, 2 star, write down the argument to see that these two guys are equal. Then use the fact that you have a sheaf, E is a sheaf, right? To just glue these data together, right? To say that actually alpha and beta are equal on any u. So that's just the main idea. You have to write it down. I won't, but that's just the main idea. So the difference really, if I want to explain, is that it is locally surjective, not surjective really. So surjection in pre-sheaves means surjection pointwise. Surjection in sheaves means locally surjective, right? So for any u, f of u to you know, your E of U, something, is not surjection, but you can find some coverage such that over the coverage it is a surjection, right? There is a formal version of it, but I won't write it down. So, okay, good.
Why is it?
It is a peak.
Why is
Yeah, it is a peak because yes, if there is no global section, right? Because it is not surjection. But locally, you can just cover the whole space such that locally you have your surjection.
it? Not getting any special property.
No, except that they are just small enough such that I have.
So if you
Homomorph.
covering this.
Yes, I don't care. Because I can't just glue everything over any covering if everything is just, you know,
Well, this is one of these trivial covers, but then interesting. I think you're reading topological covering or
I mean just the usual union, you know, between opens.
oh, okay.
Just
So
this.
is just a pickup.
Yes, yes. Okay, so you may say that, come on, I don't care about geometry. There is logic. You are right. And the problem is that there is actually no difference between the two. If you look abstract enough, you don't believe me, think about this example. And I'm borrowing this example from Samson Abramsky. So, I guess, so I'm not very good at painting, so sorry. But it should be something like this. And oh. Um, let's say that is a good picture, which is obviously not the case. Sorry. So what's the idea? The idea is that I have something here, right? And then above, I have two layers entangled, right? So let's say that you start here, you go like this, there, and then instead of going there, you go up, you go here, you go here, you go up, you come back, right? It is a twisted version of two layers, right? It's something like that stairs, Penrose stairs, whatever, right? So, okay. So you can see that in some sense, locally you have your sections, right? But globally you don't. And what does it do with logic? So the idea is actually this. So you have P here, Q here, say R here, S here. These are atoms. Let's say that you have a big set like this, that P equivalent to Q, Q equivalent to R equivalent to S. So how many? S equivalent to negation. This is inconsistent, of course. And then define your F as above on, so what is my, what is X? What's the X is just discrete say space PQRS. So this is my S1, if you like, this is my S1. And then f of any x, no, X is topological space, but it is discrete, so everything is open, any subset is open. And then now I have to define f on any open, which is any subset. And I define it as, let's say, all models of phi restricted to U. So what do I mean by that? Simply, I mean that f of, for instance, PQ means that just read the PQ part of it, and this is that, right? And then, therefore, all models of this phi PQ, which is just P. So this is a sheaf, and you can see it in this picture, right? So on this set, on PQ, this is my U, something like that U, something like this U. And then what is the section? So these two are the sections. So all models are just the ones that P equals to Q, right? So both 0. So this is just the 0 level, say. This is the 1 level, right? So both 0, both 1. The same for QR, both 0, both 1. Both 0, both 1. But if you pick this, SP, then they should be different, right? So 0, 1, 1, 0. These two lines, right? So the fact that I have no global section, or equivalently, this map is not epic, right, as in pre-sheaves, simply captures the idea that this guy is inconsistent, right? There is no global section. I cannot find an assignment. So f of the whole space is empty because there is no model, right? But locally, I have models. And my f records all local models. And we saw this before, right? If you use sheaves or pre-sheaves, you have generalized notion of valuation, right? That sometimes you don't have any valuation for your inconsistent set, but locally you record the data because it is important. What I'm saying here is that the non-existence of the global section is exactly, so this is just a logical version of a very real, so maybe not this, but so even I don't try to write it down, but there is a map, right, from S1 to S1, and the map is Z to Z squared, right? And then the problem of finding the angle is just finding the half. And then there is mismatch, right? So this twist is exactly like this twist. That is geometric, this is logical. And then what's the point? The point is that in geometry, we use cohomology theory, sheaf cohomology actually, not just to know that you don't have any global section, but to measure it. And why not here? That is the moral of the story. So, okay, whatever. The point is that if I have something that is epic in one, not in the other, it is just not a bug. It is a very important geometric feature. Or if you like, logical feature of inconsistency. So next is, okay, I have to preserve that. Next is what? Next is probably, okay, I have to say also something about the Yonedas, and then I can go to the next thing. So first, question, point. So we know that C goes to set to C opposite by the Yoneda, right? Question. For any A, is Yoneda A sheaf? And I know nothing about my code, right? It is just some site. right? Because I said that generalized space, so any simple space is a generalized space. The same question happens here, right? Now your generalized space are local, kinda. Is it the case that all simple spaces are local in the general sense? And the answer is a definite no. No, not necessarily. Sometimes they are. So for instance, here, you can check that the unidos actually are all shapes. But of course, we have the best counterexample ever, right? So we have 1J. So let's say C is a category. And you remember that 1J is one of the three very trivial. That's not actually the trivial, maybe the co-trivial coverage was that you pick something and everything, every family is covering, right? You remember this coverage. So either nothing or everything. These are two extremes. And with this extreme, because it is just a huge condition, right? You have to check all the compatible everywhere for anything, right? We saw that there is just one sheaf, and this is just a constant factor, right? There's no sheaf except just that one constant one factor, delta star. And of course, then the unidos are not sheaves, right? Because they go somewhere else. So that's not the case, and this is bad. Sometimes for some J's, it is actually sheaf. Any J where all these guys are sheaves are called subcanonical. Simply because there is something that's called canonical coverage, which is the biggest possible coverage where all the unidos are sheaves, and anything else is just a sub of that. Therefore, they are called subcanonical. Just the name to just remember, but it doesn't matter for us now. And the next thing that I have to say is maybe exponentiation. This okay, so now we know something about the limits, all exist, that's good. Co-limits, there is a problem. And something about monics, epics. But if I want to prove that that sheaf category is actually a topos, I have to provide all exponentiations, and that is not easy.
Sorry, what was the conclusion about co-limits?
We don't know that is the conclusion, right? So far, okay. So what is the exponentiation? So the obvious thing to do is just to check the exponentiation. So let's say that E and F are sheaves. And you can check the exponentiation at least in pre-sheaf. And you remember that, right? That exponentiation was extremely ugly. So let's say F to E, it should be a functor here. So define it on A, and we defined it as home on this category of unida A times E to F, right? This ugly guy again. So I defined it, I motivated it, and then I claimed, but without any proof, that if you write it down, it is actually the exponentiation, right? With the obvious evaluation. So the good thing is that it's actually sheaf. And for that, you don't even need both of these guys to be a sheaf, right? Just F should be a sheaf, and I don't care about the E, right? Am I right? Yes. So I'll explain, but yes. So if it is, yes, F should be sheaf, and I don't care about E. So claim is that for any pre-sheaf E, for any sheaf F, E to F to the E, with this definition, is actually sheaf. And first, if it is a sheaf, then you can see exactly like the limit thing that it should be the exponential here, right? It preserves So going down to sheaves, if you bring your object, since you are bringing all the maps and you respect product, right? You can see that easily that it should be also exponential object here. The only task that I have is to show that it's a sheaf, and of course I don't. But I explain just the idea of the proof. So if I want to show that this is a sheaf, I have to do this. So I have A, I have the coverage, right? And then compatible family, gluing, right? So what is an element here? So an element, right, in FEA1 is just some natural transformation, right? So an element here is simply a natural transformation here, right? The same here, there. And what I need, so let's say that this is alpha 1, and let's say that it is compatible. So it's a compatible family, A1, alpha 1, alpha 2, alpha I, whatever. And then I need some alpha from Yoneda A times E to F, right? To glue all of them together. So what should I do? It's simple, right? So you have to define it. So you have to define it on any B, right? So therefore you have to go from home BA times EB to FB. Okay, I might just, that's ridiculous, sorry. Let's keep the board, but go there. So what should I do? I have to define alpha B such that it is a natural transformation, meaning that it is from Yoneda A, EA, and Yoneda A is home EA times EA, EB, sorry, to FB. I have to come up with this map, right? And of course, I have the same for all of these guys in a compatible way if I apply them on B, right? So I have these maps, say this family. Some maps, let's say alpha I, B, from the same home B, AI times EB implies FB, right? So how to define alpha B then? I read some map here, F, and some element here, X, and I have to come up with something, right? So I have to also use the data there. But it is easy, right? You can see how to do that. Because when I have a map from B to A, right? When I have a map from B to A, this is my F, I can restrict this coverage to B, right? This is one of the properties of the coverage. So when you restrict your coverage to B, you have something that less of any of A's, right? Let's say that BJ. So let's say I have BA less than AA, B1 less than A1, B2 less than A2, something like that, right? In one-to-one correspondence, just to make it easy. And then how to come up with, how to use this data? Simple. So I have B1 to A1, which is here, for B1, EB1, FB1, right? So now I need some element in EB1, and then I can come up with some FB1, right? And the element in EB1 is, since you have something in EB, then you have something in EB1 after applying the map, and then you apply the thing, you get this, etc. That is just good. It is not that bad. It is actually the morphed version of this argument. So let's say, wait here, use another board. So the argument is actually the more formal version of, more morphed version, sorry, of this simple argument. Oh, you can see that at last, sorry, you have f of bi's, and then you want to glue them together to get something in f of b. The only point that I used E is to go from EB to EB1, and it is just enough to be a functor. So no information about E is needed, but F should be a functor. It should be sheaf. Propositionally, you see the argument, and you can imitate it for the morphed version. Propositionally, it is easier. So what I'm saying is that first, I have downsets. This is just my pre-sheaves. I have two D and say, okay, E and F, why not? Two downsets, E and F. And what is exponentiation of this? We write like this, right? What is the heighting implication? And we know if you write this down, it would be just all x's. Okay, maybe even better. The union of all downsets of A such that the downset of A intersection E is in F. You can check, I want, that this is actually the obvious version of this, the propositional version of that, right? So this is just the intersection. You see the guy, the downset. This is F, and the home is just subset, right? And then if you want to pick all of them where you have the subsets to construct F to the E, it is just a unit, whatever. So this is just the heighting implication, and claim, and of course it's downside, you can check, claim, if F is ideal, then so is E to F. Again, F is a sheaf, right? This is a sheaf. It's ideal. So how do I know that? To prove that something is an ideal, I have to prove what? I have to show that if AIs, the joint is A, and all the AIs are in E to F, then A is also in E to F, right? And if I want to prove that, so this is just this thing, right, that I have here. And so instead of having morphs, etc., I simply say that the guy is in E to F, and then I have to show that after the coverage, it is also in E to F. So how to prove that? So the main idea is this, that this simply means that AI, okay, so this means that intersection E is a subset of F for any I, and I want to show that the downset of A intersection E is in F. How to prove that? I pick an element here, B here less than A, and B is in E. This is my B, right? So, and then I have to show that B is in F. So how to do that? You do the restriction. The restriction here simply is that you say B AI is less than AI. Therefore, it is here. Since it is a downset and B is in East, so B and AI is in E. Therefore, by this, I get that B I is in F. F is a sheaf closed under this junction. Therefore, this guy is in E, but this guy is actually B conjunction disjunction of AI, and this is A, so it is B and A, which is B because of this, right? That propositional argument is actually what you have to do it in the morphed version. But in any case, so you can see that I use that F is an ideal, but I don't care about E, right? Even here. So Then I have all exponential objects same. And the last thing that you have to check to be a topos is just a sub-object classifier. But let me do something more important first. The more important thing is the claim that I had before. So I said that always you can expand a downset to an ideal. The same happens here, right? So you can expand a pre-sheaf to be a sheaf. And it has a name, the most generic name ever, sheafification. Right? You pick something and you make it a sheaf. Something is a pre-sheaf. So how to do that? Of course, I don't prove that. It is just tedious, even worse than that, case checking and etc. But the idea is the thing that I mentioned. You add whatever is needed, right? So you think of a pre-sheaf, you check a covering family, and then of course, since it's a covering family, it should come from something. That something is missing, add it up there. But you have to do it locally or twice, either of these techniques. It's called plus construction, but then you get a sheaf, right? That's the idea. But instead, I write the universal property of sheafification. So the theorem is this. Theorem is that there exists a functor A from pre-sheaves, of course, or as we prefer this, to sheaves preserving finite limits such that it is the best sheafification, meaning that, and also, okay, and a map from F to AF, and this is eta for any F, for any pre-sheaf F, such that this. So you have a pre-sheaf. This eta maps it inside a sheaf associated to F. And this is the best, the least possible. What does it mean? It means that for any, so this is a pre-sheaf, right? Pre-sheaf, make it a sheaf such that for any other sheaf and any map, like alpha, there exists a unique map alpha hat such that it's commutative, right? So it is the least possible way to expand F to make it a sheaf. You add all missing data, but nothing more, right? Right? So that's the theorem. And this A, this sheafification functor actually preserves all the finite limits. You can also check the same idea here, right? So what is the sheafification in this propositional level? So if you have a downset, what is A of the downset? It is just, add all the disjoint, all the joins such that every element is in your D, right? And then you see that it is expanding, you're adding things. You go from your thing to AF. This is the least possible. So whenever you have something that's closed under joins, this guy lives inside that. And also you respect finite limits. You can see that this operation of adding all finite disjoints, finite joins, simply preserves finite limit. The reason is just that conjunction opens up over this junction. So you can write it down. So you have this. And so that's good. because then I can prove many things just knowing this universal property without its construction. So the things that I can learn is one, A and eta are, say, unique up to either. You can prove it with this property, right? Easily. That, of course, there is just one A. So here I'm saying that there exists a functor A, but it is unique. It should be just one. The reason is that if I have A prime, then I put A prime here. A prime of F is a sheaf. I get a map. And then the other way around. And then I compose them. So I get a map from A of F to A of F. But there is just a unique map here, and the unique map is identity. Therefore, all the compositions are identity. So it's isomorphism, right? Just the usual playing with universal map. Exactly the same proof that product, coproduct are unique up to isomorphism. The same here, right? The second thing is that if F is a sheaf already, A of F actually, why not? The map from this eta map from F to A of F is isomorphism. If it is already sheaf, if you apply your sheafification, it does not change it, of course, right? You can prove it again with universal property, right? So how you say, so maybe I have to reserve that. I have to write it down here. So how to prove this? So use this universality, right? So let's say that F is a sheaf. So always you have this. Since F is a sheaf, I can put it here. I can put identity here. Then I get identity tilde, right? As a map between the two. And the composition is identity. But I have to also prove that the other composition is also an identity. And you do it via this idea, right? So you go from this to AF, you add eta here, this composition is eta. And then you say that for map F to AF with eta, there is two ways. One is this composition, the other is identity, therefore they are equal. Just play with universality, as always. The other thing that I have to mention is that the co-limit thing. So co-limit in sheaves, I mean, of some diagram, say of sheaves, is actually, you can compute it as the sheafification applied on co-limit in pre-sheaves, right? The same idea as before, right? The union of two ideals is not an ideal. Make it an ideal in the least possible way via the sheafification, and it should be your join. The same happens here. You can simply prove it. So let me just, okay, I have to say it. Let me just say it for coproduct, right? So in this sense, if I have two sheaves, EF, what is the coproduct? It is this. Of course. Right?
So, do coordinates exist?
In pre-sheaves, yes. And now, since I have a way to compute it, I know that I have all co-limits in sheaves, and even better, I know how to compute them. So compute pointwise and then apply sheafification. So I have to prove this. Let's just prove it for this one union, right? For coproduct. The claim is that this guy, sheafification on the coproduct in pre-sheaves, it is what? It is the co-product of these two. How to prove that? So of course there is a map here. This is the atom. So simply it means that there are two maps from E to this and F to this, right? And then for any other G and any map, And any map here simply means two maps from E to G and from F to G. There exists a unique map here. It is the map from the coproduct, right? So I prove that it's a coproduct.
You haven't said how you do the sheafification.
No, and I won't. That is just a mess, really. I explained actually already. So I said that how to make something a sheaf, right? What's you are lacking. So the idea is that you have a compatible family, but it doesn't come from something. Add that something. Add the compatible family to that point and pretend that it is your new element, right? But there are some subtleties about something that I don't care for now, but this is the whole idea, right? Add whatever is missing.
This is good.
Is it bad?
Okay. So well, the point is that you're showing something is a topos that has a structure like sets, so it's going to be messy at some point. I guess.
Yes.
Okay.
So already you can see that it is like sets, right? But in the logical sense, yes. So we need all these things to interpret. So I don't know. I will explain. So sure.
Yeah, so maybe this is just like a general category theory question, but shouldn't, so this sheafification is somehow universal, right? It's defined by a universal property.
I did actually. This is the universal property.
Yes. So doesn't the unit lemma already give its existence, or is it, I misunderstand something?
No. So the thing is that of course you can define many things by a universal property, but it doesn't mean that it exists. Like product, you define it via the universal property, but it does not exist always. Right? Sometimes it exists, sometimes it does not. But in this case, the whole proof is actually that this guy with this universal property exists. Yes, and you construct it via the thing that I mentioned. So, and therefore I have all co-limits. Good. The next thing, do I need this? Maybe I have to mention something. Right. So you see here that more or less what I'm saying is that all the maps from F, so fix 1F, 1E, E is a sheaf, F is a pre-sheaf, right? So then all the maps from E to F in pre-sheaves in one-to-one correspondence with all the maps from AF to E in sheaves. Right? This is what I'm saying, right? There is one-to-one correspondence between these maps. So having sheaves and pre-sheaves is not very important here. This should be pre-sheaf because F is a pre-sheaf, but this can be a sheaf or pre-sheaf because the maps are the same. Right? So right? So there is a beautiful way to say it, that A is the left adjoint for the inclusion. But since I didn't mention, and I tried so much to avoid any adjunction, I do that. But so I just pretend that I didn't say that. But this equivalence is very important because it says something. It says that there is some Yoneda version of our Yoneda lemma and our Yoneda embedding kind of here. First, let's say that you go from C to set to C opposite, and this is Yoneda. Apply your sheafification to go. So this is kind of the main idea in geometry. So work with something. If it is not a sheaf, apply sheafification, right? And then it's a sheaf, right? So you do it all the time. And the reason that it works simply because of some philosophical reasons about co-limits. But anyway, again, I'm doing this, right? So I want to go from C to sheaves, and not all the Yonedas are sheaves. We saw that. Okay, whatever, apply your sheafification. This is the least possible way to make a sheaf, right? Therefore, I have actually a map from C to sheaf. Let's say that, okay, whatever, I have a map. right? And but this map is not an embedding anymore. It should not be, right? Because again, in that example, we had an example that the sheaf is just one object. So of course it cannot be embedding, right? So we are killing the embedding, but at least we have a map, right? And the good thing is that I have also my unidal lemma in this form. So in sheaves, if you go from sheafification of the unidal, so this map, and some sheaf f, this is in one-to-one correspondence with f of a. And how do I know that? Easy. This in sheaves, you can forget a, and it is in pre-sheaves. Therefore, you have just the unidal lemma, right? It is easy. So you can read it as this is your now simple space, but locally investigated. And then all the local maps are actually the maps that you had already in your FOP. Okay, what's the point? The thing that I want to mention is that the last thing actually is that, okay, whatever, I have this. Let's keep my sheafification. Maybe it's important. But let me say this. Uh-huh.
Why does it?
What do you mean? What?
Yeah, why is there E here and then there's
Because I did a mistake. Exactly. Thanks. Always if.
yeah, it should be switched. Because we apply a on a sheet.
Yes, because I said that F is a pre-sheaf. Okay, yes. Yes, okay, yes. So since F is a pre-sheaf and E is a sheaf, then it's more appropriate to write it down like this. Yeah, they should be the same in order, but one is a sheaf or the other. So this again? This. It means that if you apply sheafification on a sheaf, it's already sheaf, right? So then you should not change anything intuitively. So this says that if you apply sheafification on a sheaf, then this canonical map that you have from your pre-sheaf to sheaf is actually an isomorphism. So you don't change your sheaf up to isomorphism, and of course it should not be, because it is just the best way to make a sheaf. So what? So they say, let's say that D is a category, whatever it is, and say I have a family F of objects. A definition. So definition. Let's say that I have a category, and then F is some class of objects. I don't care. This class is called, so we say that F generates D if you have the following property. So for any two maps, F and G, from two objects, between two objects, if for any C in F and any map, say H from C to A, F OH equals to G OH, then F equals to G. Okay, what does it mean? Simply what I'm saying is that you have two maps. You want to check that these two are equal. You have some test objects. If you consider all the maps from test objects to A and the compositions are equal, then they are equal. So for instance, in set, we have one generator, right? The generator is a singleton. if you want to check if two functions are equal, it is just possible to decomposition with all the maps from a singleton to A. So two maps are equal if they are equal on all elements. That's the extensionality, right? This is not true for set to C opposite. So here, just this, the one, the terminal is not enough as a generator because you have more information. So you can check that actually the family of all Yonedas is the generator. And here, so this is the whole point of the game. Here, the set of all of these guys are a generator in shapes. And the reason is this guy. This Yoneda. You want to show that two maps are equal, you have to show it they are equal on any A, right? Two maps here are two natural transformations, right? So let's say that I have EF alpha beta, and I have to check that these two are equal. Then I have to check for any A, alpha A from EA to FA are equal. So they should be equal on all elements on E of A, then all maps like this, right? So that's the idea. So one of the consequences here then is that I have a set, this is small because C is small, a set of generators. So let me just go a bit over time because we have to finish that. Sure. No, up to here. If for any F and G from any A to B, so D is a category, so morphisms, objects are with respect to that category. So for any two morphisms from two objects in D, always in D, and for any C, objects again in D, but in F also, for any H in D, if the composition in D are equal, then they are equal. A class of objects in D. But just objects. So I don't care about morphisms. I pick just some objects. So let me just complete this nonsense of mine. So the last thing that I have, okay, so far we see how to make a shift from pre-shift, how to compute limit, co-limits, exponentiation, and the last thing is just sub-object classifier, right? And if we have it topos. So what is the sub-object classifier already in this? You remember, it was again ugly like exponentiation. It was omega, define omega of A, because now I have opposite. So all sieves on A. And what is a sieve on A? So if I have A, sieve is just a set of maps going to A, such that if you compose something like this with a map in the sieve, it is also in sieve, right? So it is closed downward, if you like, right? And so the idea is, okay, whatever. And then, and also you can define it via pullback for any morphisms, but I don't care for now. So, and how to, so the idea is that this guy is capturing all possible values of some E inside some F. So if I have a monique from E to F, right, it simply says that E of A is subset of F of A, right, in a compatible way. And then you want a characteristic function. So you want to go from F to omega such that this characterizes how E sits in F, right? And we saw that the idea is that map F of A to omega of A, and the function is this. So you read some element in f of A, and then find all possible maps from B to A, such that if I apply f of f on X, it goes to E of B. So here is the picture, if you like. Right? So this is your A. You start here, you have some object X in the bigger one. So at some point, it goes inside E and it remains there, right? So you pick all the maps F that they backward, of course, because you have to apply your E, then your F, then it makes the object to go inside E. And this is the sieve, because if you have some morphism that makes the element to go inside E, then composition respects that, right? So the problem is that this omega is not a sheaf necessarily, right? And also you have, and the reason is that you have more information about your sieves that you are forgetting here. So let's say what kind of information I should have. If I have a sieve, right? This guy is a sieve, right? This is all the maps that makes X to go inside E, right? And it is sieve because you respect it upward. But since your F and E are sheaves, you have more information. The more information that you have is this, that if you have a cover, and if the composition maps X inside E here, 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 then already here it is in E, right? Because all of them come from one, exactly one element, right? And that one element must be also in E because E is also a sheaf. So my point is that this sieve has a closure property under the coverage. It is not any sieve, right? It has the closure property, and the closure property is this, that a sieve S on A is J closed, and J is the coverage. If you have this property, that for any covering family of, say, let's say, okay, A and A, maybe I should say B and B I's, and no, okay, A is better. So A I's and this is the coverage of Fi's. If FO Fi for any I, so all of these compositions are, say, in the sieve S, then F is also in the sieve, right? So if you cover this F somehow, then F should be also in sieve, and all of these sieves are closed, J closed, simply because E and F are sheaves. So therefore, I have to change my omega to this. Omega changes to omega J, all J closed sieves. And there is no problem because I can use the same map here because it is just already J closed, right? The only thing that I have to show is that my omega J with this definition is actually a sheaf. And this is just something that's hard to check, right? So you can check that this guy with this closure is a sheaf, and then simply because you respect all the pullbacks, etc., since it is a sheaf and it just characterizes everything, then you can prove that you have the subobject classifier with this definition. Maybe it's also good to mention that if you compute this guy in this category, then omega of any U is just the down sets of U, right? Okay. So I showed that this category is a sheaf. This category is a topos. And any category with this description is called the Grothendieck topos, as I mentioned before, right? So it is a family of toposes, right? And you can axiomatize this. So it is the construction. You pick C, you pick J, you construct it, but you can axiomatize it, right? Like the toposes, any category with these properties, right? So any category that's a topos and with two other properties is actually Grothendieck topos. The two other properties are the ones that I mentioned. One, all co-limits exist. So they say that it is so it's a topos that is big, like finite sets, for instance. The category of finite sets, it's a topos, but it is not a Grothendieck because you don't have all the co-limits. It's not that big. It should be very big. The first condition. The second, it should not be very, very big. And the second condition is that you have a set of generators. It should be constructed from some base, some site, kind of, right? So it is big, but you can control it. I am saying that these guys are Grothendieck toposes. It is possible to axiomatize them between toposes, that they are toposes with these two properties. All co-limits exist, and there is a set, so therefore small set of generators, right? Yes, you can recover J and C. So C from that, and J from some co-limits inside the category. So you may say that, okay, I have finite sets. That is just a very small category, therefore it's a topos, but it's not a Grothendieck topos. There are also other categories that are interesting that are not closed under all co-limits. But is it possible to have a very big topos then? Without that condition, right? Then you have all the co-limits, but it is just too big. There is no set of generators, right? And it is possible. I won't explain the details, but I promise that this is the last thing that I say. Pick a class G, a big, not a set, a class G, which is at the same time a group, right? It is possible. And then work with all G sets, all G actions. You can show easily that you have all exponentiations, all limits, and all subobject classifier. The subobject classifier is actually 0, 1 with obvious action, right? So you can show that this is a topos, but it is not Grothendieck. It is not Grothendieck because there is no set of generators. So essentially, the idea is that the set of generators should somehow be related to this G, and G is already very big, so you cannot control it. So it is possible to have just very extremely big toposes. Grothendieck is something in between. We are not very interested in big toposes, not very interested in small toposes. This is just the right amount of power that you have and you need. So finally, I completed. Thank you very much. And next time, June 10th, we come back with just explaining how to interpret logic in pre-sheaves and sheaves. Any question? Sure.
So is there some theory, how the Grothendieck toposes like compare in logic to the non-Grothendieck toposes?
The problem is that what the main difference between the two, other than that small generator, is just the size thing, right? You have all the co-limits, etc. So this is not a really logical thing. It is more than elementary, right? It is just second order kind of thing. It's not first order. I don't mean in the logical sense. Usually when you work with something logical, right, you cannot see the difference between the two, right? Because you cannot see the size of the universe, except that you are allowed to talk about the whole universe. And probably there, maybe you can see something, but this is not the usual approach in topos theory. Topos theory so when you interpret logic inside topos theory, you are interested locally in sub-objects of one object, not all the objects like in set theory. It is possible also to have some semantics like that, and these days people say something about that, but maybe in that respect we can see something, but I don't know actually. With the usual approach, I'm kind of sure that you cannot see the difference really.
Yeah, I guess my question is, if we're doing independence results, should I just think about these sheaf toposes or
No.
others?
Yes. Also, they are important. So let's say that you have a theory. So whenever you have forcing, sheaf kinda is enough. But sometimes you have something that's called realizability. So the idea is that you see, so it is, so in our community we call it witnessing theorems, right? So sometimes when you are interested in something like feasible interpolation, that you can witness something, you can witness provable functions somewhere, right? By that amount of complexity or growth or something, then this kind of forcing is not helpful. You have to change your gear somehow to another thing. Here, time is important. You have new notion of time, that is your C, and some coverage, whatever, right? You change things over time, but also construction is also important somehow, that you are interested in recursive functions, not all functions, feasible functions, not all functions. That is another construction of toposes, and for that you need another construction. Yes.
Check the condition about generators. So I didn't get it probably correctly. Let me try. So it's the condition is that there is a set of generators. In that sense.
Not really, but the point is, you can define the existence of, say, a class of generators. So the whole point of the definition is that what is a generator? What's a class of generators? And when the class is a set, then you say that I have a set of generators. But usually we are interested really in set of generators. Yes.
There are not too many homomorphisms between any two objects.
Yes, kind of.
That condition says that you can somehow determine homomorphisms using only
the maps from somewhere, and yes, and they are not. The reason that I'm hesitate, okay, yes, that's true. It is true, but it is true also. Okay, it really depends on the exact definition, because the exact definition is this, of course, but the intuition, we can formalize it in other ways. And then I'm afraid that it does not capture exactly this intuition. Maybe the intuition is that you have extensionality. Okay, what is extensionality? You say that two functions are equal when they are equal on all elements. In category theory, elements are not just maps from 1 to A, they are maps from something to something. These are the generalized elements. So you can say that you don't have much generalized elements. So objects have small amount of generalized elements, but generalized means just from the generators and nothing else, right? So in that sense. You had some.
So this last example said that set when G is large was an example of Grothendieck like topos when you don't have set of generators.
Yes.
Would something like pre-sheets over large category or
yeah. No. So the point is that usually we use to prove that pre-sheaves are locally small and everything is good, we use that C is small. And here I'm killing that condition. But technically you use that explanation that everything is local small blah blah to construct exponentiation because I need all the homes, all the homes, and also omega because I need all the seeds. But the good thing here, I can describe both of them just locally, and I don't need that construction. And therefore, I can just make sure that this is just reasonable class, not extremely big, even when G is big. So there's a trick. Yes. Yes, thank you.